Alright, so in this section we're going to expand the length of the element we were talking about in the previous section. Now, of course, a current carrying conductor, aka a wire, is not going to be some teeny tiny little current element, but is going to be a wire with some length that is fairly significant compared to the width of the wire. So we need to integrate over a bunch of tiny DLs in order to get the entire length of the wire. So we want to know the magnetic field strength some distance away from the wire. So I've labeled that point P. And I've labeled in essentially the magnitude of the vector here, and our x, and this is going to be our y. And I've written down our Biot-Savart law. So the first thing we're going to do here is we're going to say that dl is equal to dy. And we're going to say r equals the square root of x squared plus y squared, so Pythagorean's theorem. So this allows us to say that the sine of phi, and I've labeled phi in the diagram above, is equal to x over the square root of x squared plus y squared. Alright, so now I'm going to plug this into our law of Biot-Savart. Alright, so we're going to integrate from a to negative a, so that's essentially the length of the wire. And we're going to sub in x times dy over x squared plus y squared raised to the 3/2 power. Alright, so next we're going to integrate, and I looked this up in an integral table. Integral tables are nice. Alright, so this looks like a fairly complex relationship to use, but we have to keep in mind that typically, remember, A is the length of the wire. So if A is much, much larger than x, so typically we're looking at some distance fairly close to a wire with some long piece of wire, we can reduce the formula to this. And remembering x is the distance away from the wire. Now, we have to remember for a right-hand rule. For the right-hand rule for this one, we're going to point our thumb in the direction of dl, or the current, and we're going to use our fingers to wrap around. So if you want to see what this looks like, you can look at page 927 in the textbook. So if we have a wire where the current is going out of the page, then our magnetic field lines are going to loop around counterclockwise. So typically when we rewrite this formula, instead of using x, we use r, because this looks like it's some radius r away from the wire. This is where you should stop and complete example C at the bottom of page 2 of your chapter 28 lecture notes. I highly encourage you to attempt the problem on your own before viewing the next video where the solution will be present.